it says a net force of 10 newtons is accelerates an object at 5 meters per second. What net force would be required to accelerate the same object, so same mass, at 1 meter per second squared? So we know that Newton's second law is F net equals ma, and what you'll notice is that we have 1/5 the acceleration, so we need 1/5 the net force. Okay, notice that F net and A have a direct relationship. So if my original force was 10 newtons, then 1/5 of that is 2 newtons. So the answer is 2 newtons. The next one, it says a horizontal force is used to pull a 5 kilogram cart at a constant speed. Okay, that's the important piece. The 5 is irrelevant. The fact that it's moving at a constant speed is the important piece. So the free body diagram for this is that you have a downward force of gravity, you have an upward normal force, you have an applied force, and then you have frictional force. So if this is moving at a constant speed, the normal and the force of gravity are equal, and the applied force and the force of friction are equal. So you're told that the force of friction is 10 newtons, so this is 10, so that means that this must be 10. So we have 10 newtons. And once again, the 5 kilogram cart is irrelevant. This would be true if it was 5 kilograms or 50 kilograms or 500. And then the speed of 5 meters per second is not important. The fact that it's moving at a constant speed is. Alright, so the next one, we have the acceleration of an object plotted against an unbalanced force on the object, and we want to know what is the object's mass. So whenever you're asked about a graph question, odds are something about the graph, either the slope or area, represents something physical. So we have the acceleration versus force. So what you need to do is find an equation that has acceleration and force in it. And so we know that acceleration equals F net over m. Okay, so that's Newton's second law. And if I rearrange that and solve this for m, I have m is equal to F net divided by a. So what I'm going to do is I'm going to pick a point where I have an F net and an a. So in this case, 2 newtons and 4 kilograms. And I get a mass. Oh, sorry, this is not 4 kilograms. This is 4 meters per second squared. And we get a mass of 0.5 kilograms. And that's my answer. And notice that if you do this for any 2 points, this would be 1 over 2. If you do it up here, this would be 3 over 6. So you get the same answer no matter what point you pick. 0.5 kilograms. 39, it says a diagram below shows a 5 kilogram block at rest on a horizontal frictionless table. Which diagram best represents the force exerted on the block by the table? So we're talking about the normal force. So if I had to draw a diagram of this, we have the downward force of gravity that's from the earth, and then we have an upward normal force from the table. So this is what we're asking about, and since the block is not moving, these two are equal. So I can find the force of gravity because I'm given the mass, right? And I know it's a mass by kilograms. And if I take my 5 and multiply it by my 9.81, I get 49.1 newtons. So A is my correct answer. Alright, so next we have a mosquito flying over a highway, strikes the windshield of a moving truck. Compare the magnitude of the force of the truck on the mosquito during the collision. The magnitude of the force of the mosquito on the truck is, well, this sounds a lot like a third law that states the force of object A on object B is equal to the negative of B on A. So the magnitude is the same, but the fact that it's negative just means the opposite direction, which is not being addressed here. So the forces on the two are the same. Now you may be thinking, well, how could this be? But remember, what you see is the acceleration. So even though the mosquito pushes on the truck as much as the truck pushes on the mosquito, so they have the same net force, the mosquito has a much smaller mass. So they will have a much larger acceleration. So the cause is the same force, the effect is having a much larger acceleration, this is what we observe, right? So the forces are the same, the accelerations are not, and that's because they have a different amount of mass, different amount of inertia. 41, it says a 1 kilogram object rests on a horizontal table. The force that the tabletop exerts on the object, well, this is very similar than before, that the normal force is equal to the force of gravity, okay, if you draw a free body diagram, and this could be found by m times g. So I take 1 and I multiply it by 9.81, and I get 9.8 meters per second. All right, the next one, we have 2 satellites of equal mass, and then they're circular orbit around a planet. Compare the magnitude of the gravitational force of attraction between satellite A and the planet and the magnitude of the gravitational force of attraction between B and the planet. Okay, so this sounds a lot like the universal gravity, and this is a proportion problem, Gm1 m2 over r squared. Satellite B is twice the distance away, and since its distance from the center is twice as large, its force of gravity would have to be down, and it's down by the square of the same factor, meaning that if I double this side is going to go down by a factor of 2 squared, so it would be 1/4 as great. When a satellite is a distance r from the center of the Earth, the force of gravity is F. What is the force of the satellite when it's 3r? So same idea. The distance is getting bigger, so conceptually I know that the force gets smaller. So I'm getting bigger by a factor of 3. So I have to get smaller by a factor of 3 squared, or 9. So this is F over 9. All right, this one's a little tricky, and you have to imagine we have the Earth, right? The Earth has some radius, and we have an astronaut standing on it, not to scale. Okay, and they are originally an Earth radius away from the center, meaning that when I stand on the the surface of the planet, I am the radius of that planet away from the center of the planet. Okay, the short and sweet version of this is that if I take that astronaut and send it another Earth radius away, I have effectively doubled the distance from the center. And if I double the distance from the center and I want to talk about the forces, same as we saw before, the force of gravity gets cut by a factor of 4. So if this is 800 newtons on the surface of the Earth, then my new force is going to be 1/4 of that, my new weight, or 200. Right? Now, you can actually go through this calculation. You can actually calculate it. G would be the 6.61 times 10 to the minus 11. M1 would be the astronaut's mass, not its weight, so you'd have to find the mass from this, F of G equals mg. Then you can look up the mass of the Earth in your reference tables. And then what you need to do is recognize that they have gone twice the Earth the 2 Earth radii away from the center. So this would be 2 times 6.37 times 10 to the 6. And this number, if you're curious, okay, this is right in your reference tables as well. So that's how I recognize that I have effectively doubled my distance from the center. So a couple different ways of solving this problem. All right, the next one, it says force between distance. Well, anytime you're trying to sketch a graph, you want to think about the equation. So we have F of G equals G m1 m2 over r squared. And since we're graphing just force and distance, and I have force on the y and distance on the x, I'm just going to put x and get rid of the other stuff. You could write it as 1, where my x-axis is. And you can actually throw this in your calculator. Look at what the graph of y equals 1 over x squared looks like, and you will see the inverse squared graph look like so. All right, 46, we have a 50 kilogram student standing on the Earth with the force. Okay, so they're standing on the Earth, so we know G, so we could just simply do F of G equals mg. And so this becomes 50 times 9.81. So that works out to be 491 newtons, or 500 roughly, if you call G10. What is the gravitational acceleration? Okay, so we're looking for g. G is our unknown. 2 kilogram mass, so m equals 2, and it's got a weight of 16 newtons, so the F of g is 16 newtons. So this is once again an F of g equals mg, but we're solving now for g, so g equals F of g over m. So this is 16 over 2, or 8. Now you could write this as either newtons per kilogram or meters per second squared. Nice little kind of proof is to prove that these two are equivalent, and it forces you to remember what the newton is equal to. Alright, so another proportion problem. If the mass of an object would double, its weight would be. This is a little bit easier than the other ones, but if I double the mass, I double the weight. Direct relationship between weight and mass. Here is a graph of weight, which is, weight is a force of gravity versus mass. Now, once again, you're either going to be looking at the slope of this graph or the area of this graph. Find an equation that relates the two. So I have F of g equals mg. Notice that this is a direct relationship, right? It's a linear. Okay, so I can rearrange it like this. Alright, and the reason why this is important is that this is what I have on my y-axis, this is what I have on my x-axis, and this is my slope. So, if I want the acceleration due to gravity, find the slope. Okay, so maybe I'll use 2 points here. Okay, you can use any 2 points. And so I'm going to do the slope is equal to the rise over the run, or 24 minus 8 newtons over 15 kilograms minus 5 kilograms. And that is 16 over 10, or 1.6 meters per second squared. Okay, so the next page, we have a parachute that skydivers jumping up. The upward drag acting on the parachute is equal in magnitude but opposite in direction to the weight of the parachutist and the equipment. As a result, the parachutes will be moving. Okay, so this force and this force are equal. So if they are moving, they're going to continue to move at a constant speed. So I can get rid of, actually, that gives me my answer. So not only are they moving downward, but they're moving down at a constant speed. All right, in order to keep a 20 Newton moving, an object weighing 20 newtons moving at a constant speed, it is required 10 newtons worth of force. The force of friction. Okay, we've seen something. We saw something like this earlier, where we have a downward force of gravity, we have an upward normal force. I don't know why all my normal forces are slanted. And then we have an applied force and then a frictional force. So these are equal and these are equal. So if I know that this is 20, which is not, this is not asked about, we're asking what is the force of friction, so that is equal to the applied force, or 10. So the answer to this is 10 newtons. Alright, so this is a nice little friction question. So we have a block of wood, same mass. One has a bigger surface area touching, and then one has a smaller surface area touching. And if you guys recall, with the friction lab, we saw that there was surface area does not affect the amount of friction. So same answer, 10 newtons. What is the minimum horizontal force needed to start a 300 kilogram steel block on a steel table? Okay, this is not just extra information. Use the reference tables to find up the coefficient. And minimum force needed to start the moving, meaning it's not moving already. So the static force of friction, or sorry, static coefficient of friction is 0.57 for steel on steel. And so we have the fun equation, right? Mu times the normal. And it's a flat level surface, so the normal force is equal to the force of gravity. So this is equal to mg. So this becomes mu times m times g. Plug in the numbers. We have 0.57 times 300 times 9.81. And when I threw these numbers in, I got a value to 3 sig figs of 1710 newtons. As more force is applied to the steel box sliding on a steel surface, the coefficient of kinetic friction will. So this, and I just had to read that again, it's saying that the box is already moving. And so if it's going faster, one of the other things that we saw in the lab is that the speed does not affect the amount of frictional force. I mean, notice that in the fun equation, right? There's no speed factor. So yes, the box will be sliding faster, but it would remain, the coefficient, which is really a description of the roughness of the surface, that won't change. All right, and last one on this page. This is more of a, second to last one on the page. So 55, Jill is pulling a 200 Newton sled through the snow at a constant velocity using a force of 10 newtons. What is the kinetic coefficient of friction? Okay, so we have to kind of go back to the diagram. Okay, same diagram as before. Let's see if I can get my normal force straight up. There we go. And then it's moving at a constant speed, so I know that the applied force is equal to the frictional force. Let me shorten that a little bit. Okay, so these are equal to each other, and this is equal to that. So we're told that this is 200, and so that is 200. We know that this is 10 newtons, so this is 10 newtons. So what we're asked to find is the coefficient. We're asked to find the mu. So we know the fun equation is equal to mu times the normal. Okay, so I basically need to know the normal and the force of friction in order to find the coefficient. Right? Do a little bit of algebra. The coefficient is the frictional force over the normal. So this is 10 over 200. Okay, so then 1 over 20 would be 0.05. All right, and then the last one, this is just a reference table question. Which road surface offers the greatest traction? Okay, with rubber tires. So just go look at the rubber on dry asphalt, dry concrete, wet asphalt. You will see that dry concrete has the greatest coefficient of friction. All right, so next one, the map below, so we have to figure out distance and displacement. Okay, so remember, distance is what your feet would feel. Displacement is your change in position. So the distance would simply be 400 plus 500 plus 400 plus 500, and that adds up to 1,800 meters. And then the displacement is how far did you end up. So it's a straight line between here, the starting point, and your ending point. So if this is 400 and this is 400, the displacement is 800. This is all meters. And even if you want to add in your direction, let's assume north ups. Let's assume the compass is north, south, east, west. Then this would be 800 meters east. All right, two 30 Newton forces act concurrently on an object. In which diagram would the force produce a resultant of a magnitude of 30 newtons? So if I wanted to figure out which one of these I would get a resultant of 30 newtons, then what I could do is I could simply draw these arrows so they're tip to tail. So I'm going to copy this one. I'm going to copy this one. Now we don't really need to do this with a ruler and protractor, but we notice that this line is longer than the other two. Okay. Similarly, if I copy the other vector here, you'll notice that the resultant is longer than the individuals. Okay. But when I copy this one, okay, and you can kind of get a sense of this based on what you know from your math class. If there's 120 degrees here, then there's 60 degrees here, and then that means there's 60 degrees here, and then that means there's 60 degrees here. Okay, so this is your classic equilateral triangle, and so that is also 30 newtons, and so that's our answer. All right, 59, it says a 5 Newton force and a 7 Newton force act currently on a point. Okay, so all this means is a fancy way of saying is that it acts on the same point, at the same spot. Okay, like these two vectors. These are two vectors acting concurrently because they're acting on this point. So if I wanted to figure out what the as it goes from 0 to 180, the magnitude of the result. So when they're at 0 degrees, then they're lined up with each other. So if I have 5 and then 7, okay, this has a result of 12. Okay, and then if I have 5 this way and then 7 that way, I'm going to go off screen, then I have a resultant of, we could say, minus 2 newtons. Now, we're just talking to the magnitude, so the fact that it's negative is really relevant. So it's going from 12 to 2. Okay, remember that these two forces can have a max when they're added together and a min when they're subtracted, and then we can make any number in between, giving that some angle between them like this up here. So if we want to figure out the resultant of these two forces, or the result of this, so what I could do is I can copy this vector, okay, the 12, and I could also copy the 5 since they're acting at right angles to each other, or there's two of them. And so what I could see is the resultant would go across the triangle, okay, in that direction. It's important. And then I could solve this using a squared plus b squared equals c squared. So this is 5 squared plus 12 squared equals c squared. So I got a resultant here, magnitude-wise, of 13. And that's rounded to 2 sig figs. I believe it's 13.1, but you can check your calculator on that one. All right, the last one, which vector diagram best represents a cart slowing down as it travels to the right on a horizontal surface? So in order for it to slow down, it has to have a force in the backward direction bigger than the force in the forward direction. So in this case, you see that these forces are balanced, these forces are balanced. Here we have both of them being unbalanced. Notice this is the frictional force. So it means that in this case, the cart is moving to the right. And then in this case, the cart is moving to the left. So this is our one where we have a force moving, excuse me, I'm going to back up a second. Since the applied force is in the forward direction, this one is actually moving to the right. So this would be a situation where you're moving to the right, but since the F net is to the left, your acceleration is to the left. This equates to slowing down. Okay, which is what it's asking.